So, now we will talk about symmetries and conservation laws and their tests. Uh, Symmetry is intimately connected to conservation laws, and this was shown by the mathematician Emmy Noether in 1918. She showed that every continuous symmetry leads to a conserved quantity. So, for instance, the conservation of linear momentum comes about from translational symmetry. So, if things look the same here and at a displaced object or when you displace the coordinates by a certain amount, if they look the same, then this leads to the conservation of linear momentum. So, similarly, if you have a rotational symmetry, then this leads to the conservation of angular momentum. Temporal symmetry, which means if things look the same, if they are displaced in time, then this leads to the conservation of energy. So, these three fundamental conservation laws actually were shown to arise from symmetry, which is a great idea. There are examples, of course, of continuous symmetries, which with respect to, let's say, infinitesimal displacements in spatial displacements or angular displacements or temporal displacements. And there are also those symmetries where you have discrete symmetries. So, it is in some angle in some other space. Now, symmetry with respect to a local phase transformation is called the gauge transformation, is actually a very powerful device to even give a structure to the Lagrangian or Hamiltonian, as the case may be, for the electromagnetic interactions with charges. One fallout of this, of course, this symmetry with respect to gauge transformation, is that electric charge is conserved. Now, as I said, symmetry with respect to a global phase transformation, that leads to conservation of a baryon number, let's say strangeness, charm, and other flavor number conservation, like the lepton number conservation and so on. Or if you have these other quarks called bottom and top quark, so those things are conserved in strong interactions. Of course, some of these symmetries are broken in other interactions, like in the weak interaction. Of course, you have strangeness number violation when you have a weak decay. So, you can have a lambda going to a neutron plus something, and lambda has strangeness, whereas neutron doesn't have strangeness. Examples of these energy momentum conservations are that if you have a photon interacting with the nucleus, then you can have pair production. So, this is shown here. You have a photon interacting with a charge, and that gives you E plus E minus. Here Z is the nucleus. Of course, if you have a photon, can it go to E plus and E minus in vacuum? No, because this violates energy momentum conservation. Okay. Similarly, a neutron decaying to a proton, a electron, and an anti-electron neutrino, this is allowed. But a neutron going to a positron, an electron, and an electron type of neutrino is not allowed, because you are violating both baryon as well as lepton number. Energetically, this is allowed. You can also take care of momentum conservation and so on, angular momentum conservation, but this is not allowed because B and lepton number are not conserved. Similarly, a neutron going to a proton and a neutrino of the electron type, let's say, and anti-neutrino of the electron type, this is also not allowed, because here you are violating electric charge, and we will talk about that a little later, experiments to search for such electric charge non-conserving beta decays. Because on the left hand side you have charge 0, on the right hand side, since the neutrinos are neutral, you have plus 1 charge, plus 1 electric charge. So, this is not allowed as far as we know. Okay. Now, a very little bit of theory just to motivate what we are going to do a little later. So, if the Lagrangian, which describes the system under consideration, the quantum mechanical system, of course, it's also, you have Lagrangians for classical systems. So, if this is invariant with respect to translation in time, then you have this dl by dt, the partial derivative is equal to 0, and this actually leads to derivative of the Hamiltonian with respect to time, this is 0, this is the conservation of energy. So, you can show that by taking a derivative and in terms of partial derivatives, because the L depends on q dot, rate of change of the generalized coordinates and time, and if you use the Lagrange's equations of motion, you can show that dH by dt is 0. Uh, that is the energy conservation, the law of conservation of energy. Now, as I said, the demanding invariance with respect to a gauge transformation actually leads to the structure of the Lagrangian with the electromagnetic field and charged particles and the interaction between them. Okay. So, if the Lagrangian is, for instance, written down by this, those of you who have not studied field theory, you can skip this slide. So, it's written in terms of gamma mu's and the partial derivatives of the spinor wave function, and then a mass term. Now, if this has to be invariant under a global gauge transformation, psi e to the I theta, you can put this down and you can see that it is indeed invariant under a global gauge transformation, okay, because of the psi bar and the psi terms coming in, and this theta is just a real number. Okay. However, what happens if theta is a function of x? So, this is a local gauge transformation. Okay, so for a given x, this is a number, but this number can change as a function of x. Now, if you see this, you get an extra term here. Lagrangian becomes Lagrangian minus derivative of with respect to theta, and now theta is not just a constant. So, partial derivative, of course, theta is not a constant, but depends on the spatial coordinates. So, now you have to do something else. So, you have to actually cancel this term with an extra term, and this involves the new gauge field. But of course, if you put a gauge field like this, a mu, it no doubt cancels that extra term, but then you can have it interacting, it gives a mass term in the Lagrangian. So, this is shown, I think, in the next slide. So, if a mu goes to a mu plus derivative with respect to lambda, lambda of course being a function of x, and this is related through this, lambda x is h cross c by q times theta of x. Then the full Lagrangian, because in principle this gauge field could have a mass, and so there is a mass term which is added. So, of course, this term which is f mu nu times f mu nu, this is a product to give you a scalar quantity. Then this first term is invariant under the gauge transformation, but the second is not unless M A is 0. And then of course, the complete Lagrangian becomes this, and this is actually the electromagnetic Lagrangian. So, if you demand gauge invariance, not only do you get the full Lagrangian, the structure of it right, but you also have to say that the mass term here is 0. So, in this case it turns out that the quantum of the electromagnetic field is a photon, and then that mass of the photon has to be 0. You also get a conserved current density. So, this J mu is the current density, and then the divergence of this is 0, which means the divergence of J, this is in 3 coordinates, and in time this is just the change of the electric charge density. This implies the conservation of electric charge. So, now we will come to experiments that look for such things. So, the whole idea of testing these conservation laws was articulated very nicely by Maurice Goldhaber and Feinberg in one of their papers in 1959, where they say that the basic principles of theoretical physics cannot be accepted a priori, no matter how convincing they may seem, but rather must be justified on the basis of relevant experiments. So, and this became particularly important in the context of parity, because everybody believed till it was suggested that maybe parity is not conserved in beta decay. Till then, everybody has assumed that parity has to be conserved. I mean, it was taken to be just a basic thing, and everybody believed that it has to be conserved. But after that time, then people started, for instance, this articulates that thought that maybe we should look at all of these conservation laws critically through experiments. So, there are of course experimental tests of conservation of electric charge. We don't know of any instance where it is violated, but still we would like to search for a possible non-conservation of electric charge. So, what is the conservation of electric charge? The charge initially is the same as, let us say, after a decay is, if you look at the sum of the charges in the final state, then the sum is equal to those in the initial state. So, for instance, take a lead atom of lead. If the electron in the K shell suddenly disappears, then of course this becomes a positively charged ion. It would lead to emission of a lead K X-ray, and you could look for that. Similarly, if the proton in a nucleus disappeared, there would be a neutron or a gamma ray emission, and these are examples of, for instance, of lepton, baryon number violation, of course, and you could look for such things. Specifically, I will talk about one example where we looked for the electric charge non-conserving beta decay, and in the case of rubidium 87, you can go to 87 strontium plus 2 neutrino and antineutrino. You can see the charge is not conserved in this process. Okay, and we'll see the level diagram for this. So, if for instance you have 87 rubidium going through the charge non-conserving beta decay, then it can go to an excited state, because then you you don't need an electron in the final state, which has about 511 keV rest mass. So, you can populate this state, which you couldn't otherwise populate if you had only electric charge conserving beta decays. So, if you have an electric charge non-conserving beta decay, then you would populate this state, and this state could be looked for. So, this is the basic idea. So, you take some amount of rubidium salt and then extract after a certain time, which is of the order of let us say a few times 2.8 hour half-life of this state, and you do some chemistry, and you make sure that there is no rubidium in that. So, you can make a very thin source of this, and then we looked for it through a convergent electron K X-ray coincidences. This was, you could have looked for the gamma ray as well, but then a gamma ray measurement, let me go back to this slide. If you were to measure the gamma ray here in singles, then there is a large amount of background which you have to contend with. Whereas, if you looked at the conversion process, and this is perfectly possible because this is a M4 transition with a large conversion coefficient, then you can look at not only the conversion electron, which has an energy of this transition energy minus the binding energy of the K electron, but you can also look for the K X-ray. Now, this coincidence means that you have you can reduce the background in such an experiment. So, this is the detector setup. I won't go into the details. Suffice it to say that there are two silicon lithium drifted detectors of large area, diameter about 28 to 30 mm and about 2 to 3 mm thick, housed in a cryostat. So, you have a cold finger which cools these detectors to reduce the noise, and it is in a steel cryostat. It also has lead shielding around it, and lead and iron shielding. So, you have some amount of lead here, and then you have some amount of iron, and so on, so as to reduce the background that could enter into this detector. So, this is actually, I made a mistake. This is the stainless steel shielding, and this is there is some amount of lead as well given by this hatched part. Okay, so we make a thin source of this strontium. Maybe I should go back again here. This is a level diagram. So, you try to extract strontium from this sample. Of course, there is some naturally occurring beta decay, but that is extremely tiny because of the large half-life, 10 to the 10 years. So, if you populate this, you will get some amount of strontium. So, you remove strontium from this sample, make a very thin source because convergent electrons should not lose too much of energy and so on. Okay, so having done that, then just to show that the detector works, these are convergent electron spectra of indium-113, and you can do the same thing. You can do a convergent electron K-X-ray coincidence, make sure that everything is working. And then you take spectra with separated 87M strontium from natural rubidium, and dummy source as well, because this might have some other, perhaps some radioactivity in the process of doing some chemistry. And so we look for this zone where convergent electron plus K-X-ray, and you don't see anything in that region. So we can put a bound. This is there in this paper of 1983. Now, from the upper limit on these counts in this region, then you can put a bound on the half-life, a lower bound on the half-life, and then a branching ratio of the charge non-conserving decay to the charge conserving decay, and this is of the order of 10 to the minus 20 or so. This was an improvement over the previous experiment by about a factor of 40. When the gallium detectors came online for solar neutrino detection, then of course that gallium detector was in the range of tens of tons. So this, whereas we had only of the order of kgs amount. So this improved this the CNC bound, because you are looking for a similar situation, that if you have charge non-conserving decay, then you have gained that much more energy. You can populate 71 germanium through this state. And since the neutrino, solar neutrino also produces this, of course, to maybe make a few or so per day, but then you can say that this, part of this could be due to charge non-conserving decay, and you can put a bound on that. And you can see that this bound is an improvement on what we got by several orders of magnitude, of the order of actually 6 orders of magnitude better. This is in this paper, Norman Bacall and Maurice Kuldhaber in 1996. Similarly, people have looked for baryon number violating processes, because theories that unify the electromagnetic weak and strong interactions lead automatically in most of these theories to a baryon number violating process, baryon decay. So proton decay, so this came to be known as the proton decay experiments, set of experiments. And the Kolar Goldfield experiment in India was the first to get off the mark. Unfortunately, the protons don't seem to decay, so they could only put a lower bound on this mean life of the proton. Much bigger detectors. So this, I think, in the last stages was about 350 ton. But with the super Kamiokande coming in at 50,000 tons and counting also for a much longer time, they could increase this lower bound to about 10 to the 33 years or so. Now, of course, there are other experiments, hyper Kamiokande and so on, which are another factor of 10 bigger, and so people are still looking for or searching for baryon number violating processes. Similarly, charged lepton flavor conservation has been looked at. So you can look at muon number conservation or electron number conservation, and this is the way people have looked for it, muon going to electron plus photon. This can be done also in a bound state, bound atomic state. Muon gets captured on titanium, and if it goes to an electron, then of course you get an energetic electron, and you can look for this. And this was the branching that was measured. So there is only an upper bound. It can be smaller than this, of the order of a few times 10 to the minus 12. Now there is presently an ongoing experiment at Fermilab called mu2e, which hopes to discover such a decay if nature permits. Of course, if this is there, then they are sensitive to a branching ratio if it is greater than 2.5 10 to the minus 17. So this is almost like 5 orders of magnitude more sensitive experiment than was there before. And if the branching ratio is of the order of about 10 times larger, then they can even measure it at 5 sigma confidence level, which is, this is the sort of gold standard for high energy physics. Okay. So in summary, we have stated the connection between a symmetry principle and a corresponding conservation law. We have illustrated it with gauge invariance in electromagnetism, and then we have talked about conservation of electric charge, experiments to put bounds on that, and we have described an experiment of course, this experiment involved looking for conservation of electric charge in beta decay, which was done here in Mumbai, at TIFR in Mumbai. I have not in this case talked about the other major consequence of imposing gauge symmetry, namely is the photon massless. So, there are presently bounds on that, which are bounds of the order of 10 to the minus, I think 50 plus electron volt by c squared, which use a variety of physical phenomena. If you have a photon which is having a non-zero mass, then of course you get a Yukawa like interaction, except that the range of this interaction is huge. It runs into thousand, not even thousand, millions of kilometers. So, from the way the magnetic field of Jupiter, let's say, varies as a function of distance, people have put bounds on the possible mass of a photon and so on. So, but in this talk, I have not talked about the possible bounds on the mass of the photon. Okay. Thank you.